can always transfer from the
Oh, no, it's
Most of the places. Most of the places, yes.
just not it.
Okay, guys, let's go to page 3. Let's just do a few more problems for practice before we move on to the next topic. So page 3, let's look at number 9. So go ahead and read that problem, give that a try. Now I'll go over it once we have a chance to try it. But we'll try number 9, 10, and 13. So 9, 10, and 13. Okay. Page 3. Okay, so number 9, we're going to apply integration by parts. We know integral of fg prime is equal to fg minus integral of f prime g. There's going to be bounds involved, but we know that we can just go ahead and fill out the right side. This side is taken care of, or this portion is taken care of by what's given to us in the problem. We just have to evaluate the definite integral, the bounds between for fg from 0 to 3. So this is already the completed antiderivative. We just have to plug in 3 and 0, f of 3, g of 3 minus f of 0, g of 0, and then we can use our table to help us get to those values. That will give us 15 plus 4, and then this is a 6, so minus 6. Okay, for number 10, let f be a twice differentiable function with selected values. What's the value of the dash integral from 0 to 3 of x f double prime of x dx. Anytime that I feel like I can take advantage of tab method, I like to use it. Okay, everybody okay with number 9? Everybody good there? Okay, you line up your first column and your second column. Your first column is x. X will go to 1, 1 will go to 0. On the g side, which is have to take the antiderivative, f double prime rises up to f prime, rises up to f of x. Make sure that that you are changing the signs. So the first term is always a times +1. I put a plus there, followed by a minus, followed by a plus, and then you're multiplying diagonal terms starting with the upper left term. So x times f prime minus f of x. That's your antiderivative. You can evaluate that between 0 and 3 because we have to involve our bounds. Upper bound first, minus lower bound, and then the rest just use your table to help you get down to your numeric answer. Okay, let's finish off this section with 13. Try 13. Okay, if we match everything up from our formula, we can tell that the last portion is integral of f prime g. So you know f prime must be 1/2 x cubed. And if f prime is 1/2 x cubed, we can work backwards to figure out what f is. So if we take the antiderivative of f prime, we get 1/2 times x to the 4th over 4, which is x to the 4th over 8, and that must represent f. Right, any questions? Okay, let's go into today's notes, page 5. We're talking about linear partial fractions. Okay, we also call this partial fraction decomposition. The idea is that if there's a messiness in the denominator of your rational function, we're able to decompose or break them down into the sum of separate fractions, and idea is that it'll make it easier to integrate if we're able to take a messy problem and break it down into smaller parts. So it says let f of x equal p of x over q of x. Let that be a rational function where p and q are polynomials. If the degree of the numerator is smaller than the degree of the denominator, then you might be able to use partial fraction decomposition to change the integrand, that's the expression before the integral is taken, to something easier to integrate. We can decompose this fraction to make it easier to integrate. Okay, so all this messiness is to say that if we want to, using the process of partial fractions, our hope is that we're able to get it into this form. We get it into a sub 1 over a sub 1x plus b plus a sub 2 over a sub 2 of x plus b. Basically, we're taking the denominator expressions and breaking it into smaller parts. Okay. So we want to make each factor a separate denominator. So I have two ways of doing partial fraction decomposition. I'll show you the way that maybe is the way that's presented, and then also show you the shortcut method, which I like more because you don't have to do as much writing, and it's a little bit faster, but it's also, you have to remember a few more steps. So I'll go through both, and you guys can pick and choose which one you want to use. But I think for me, I like the shortcut method better. It allows me to get to the expression a little faster. You just need to practice those specific steps. But let's look at number 1 here. Number 1, you have 1 over x minus 1 times x plus 2. This problem will be a lot easier to work with if I can get it into two fractions as something over x minus 1 plus something over x plus 2. So that's the goal here. The goal is to represent this fraction. Sorry, x minus 1. So right now, we're not even going to worry about the integral. We're just trying to get this expression to look a little cleaner. So what if I can represent this as some value over x minus 1 plus some value over x plus 2, right? I'm going to have a much easier time integrating this than this, assuming that a and b are just constants. Then this is just an easy integral 1 over u du, right? Just easy natural log and integral rather than this where you have to go through some additional steps. So that's the goal here. What can I find for A and B that will represent where this is the same thing as this? Then that way we can replace this with this problem, and then we can just find the integral of an easier problem. That's the hope. Now, if I want to figure out what A and B are, I'm gonna have to do some algebraic steps here. So what if I did this? What if I multiplied everything through by x minus 1 times x plus 2? That way I can get rid of the denominator, get everything up to the numerator, and I can just use some steps to help me isolate A and B or solve for A and B. So if I distribute this through here, start with the left side here. If I distribute this through here, what am I going to get? Everything cancels out, right? Numerator and denominator cancels out, so I'm just going to get 1. 1 equals, if I multiply this with A over x minus 1, then what do I get? Times A. Yep, the x minus 1 cancels out, but I'm left with A times x plus 2. Plus, if I distribute the x minus 1, x plus 2 through, what am I going to get? Yeah, the x plus 2's cancels out. I'm left with B times x minus 1. Okay, I'm going to solve for A and B separately. I'm going to find a way to get rid of A so that I can focus on B. So we're forcing one of these to be 0, so I can solve for one at a time. Let's strategically pick something that will get this to go away. What can I pick for x? -2. So I'm going to force this to be x equals -2. Okay, and that will hopefully get this to go away, and I can solve for b, right? So if I replace -2 in for x, I get 1 is equal to a times 0 plus b times what? -3. Okay, this goes away. So if I solve for b, b equals what? Yeah. Okay, let's revisit this expression. But now let's use x equals what? 1. Yeah, we're going to purposely choose the x value that will get rid of b so we can focus on a. So I'm going to choose x equals 1. Okay, so plug 1 into the same expression. A equals, sorry, 1 equals a times 3, so a equals what? 1/3. And then if I have -1/3 for b, and if I have 1/3 for a, then I can just take the integral using natural log and getting to my answer. Okay. So that's one method. That's perfectly fine. I want to show you another way of getting the a and b value, and this is called the cover-up method. So here's the cover-up method. I'm going to go back to this expression here. So I'm going to force this to go away. So again, let me say x equals 1 here. So the cover-up method allows me to do this. If I choose x equals 1, okay, I'm going to cover up the x minus 1 that's associated with it. I'm going to plug 1 into the remaining x. So 1 plus 2 is what? 3. 1 over 3, that's 1/3. 1/3 is equal to a. Feels a little bit faster, but it does require that little gimmicky thing of having to cover up and plug in. So that's how I can get to my a. Now to get to my b value, I'm gonna force an x value that will make this go away. So I'm going to choose x equals -2. Now, once I do that, I'm going to cover up the x plus 2 because I don't want that to influence this x plus 2 here. I cover up that x plus 2, plug -2 in for x. What is it? What will that give me? -3. So -1/3 is my b. That's my b value. Okay. So either way, I like the cover-up method because it just allows me to get to my a and b value a little faster. But this is fine as well.
Does it always work?
Yeah, so it always works for linear. And those are the only ones we're having to worry about are linear partial fractions. So that's good. Is that it doesn't work for every scenario, but we're never, for us, we don't have to worry about quadratic partial fractions. So that's good. It can work for anything that AP exam throws at us. Okay. And those are the only ones you have to worry about, even though the book does go into more complicated versions that we don't have to do. Okay, so my A value is 1/3. My B value is negative 1/3. So I'm substituting this problem with what we think should be an easier one. Now, this is just simple U substitution problems. If I let my U value be x minus 1, let's handle these separately, then my du dx will just be, or dx would just be du will be dx. So I'm just left with 1/u du with the coefficient of 1/3. So this ends up essentially giving me this, which will turn into 1/3 natural log absolute value of x minus 1. Okay. What do you think the result of the integral of this would be? Negative 1/3 natural log absolute value of x plus 2. And that's it. That's our answer.
Plus C.
Good, plus C. Another variation. Now, this is perfectly acceptable if there's free response or even on test. But sometimes on the AP exam, they may try to combine this a little bit more using log properties. So we could think of this as natural log of A minus natural log of B. So we can make that natural log of A over B. So another way that can be represented is 1/3 natural log absolute value of x minus 1 over x plus 2. Either is fine, but I just want to make sure that you're able to understand this is also a valid solution. So if it's multiple choice, and if you get to this answer, that if this was your answer choice, that you can get from here to here. Okay, if you guys are okay, I'm just going to stick with the cover-up method, especially if there's more than 2 linear terms. It just feels a little cleaner. I can just quickly get to my A, B, and C values a lot faster. But if you're comfortable using this way, by all means, you can go through that, and that's perfectly fine. Okay, so let's look at example 2 here. We have 2x squared minus 7 over x cubed minus 3x squared minus 4x. You know partial fraction is an option if the degree in the denominator is higher than your numerator. Okay, so because of that, I'm going to try to factor the denominator out to see if I can get the denominator to show me a bunch of linear factors. So I'm going to just work on my denominator here. X cubed minus 3x squared minus 4x. I can factor out an x. And continue factoring. Okay, so the hope is I can get this fraction or get this one fraction to be a over x plus b over x minus 4 plus c over x plus 1. Okay. So I'm going to focus on the algebraic portion first before we can get to the calculus. So every factor will get its own fraction. Okay, so to find what you want to use, you want to set your denominator equal to 0. So in this case, I'm going to test what? X equals what first? 0. Okay, so to test x equals 0, you're going to do the cover-up method. You're going to cover up one of the factors in the denominator, the one that's going to cause it to be 0. So I'm going to cover up the x. I'm going to replace all remaining x's with 0. So numerator and denominator. So numerator, I get what? -7. Denominator, I get 0 minus 4 times 0 plus 1, -4. So my A value is just 7/4. Okay, next up, set x minus 4 equal to 0. I get x equals 4. That's the number I want to test. That will help me get to my B value. Cover up your x minus 4. And then replace 4 in for all the remaining x's. 2 times 4 squared minus 7. That's 2 times 16. 32 minus 7 is 25. Plug 4 in for the x's. I get 4 times 4 plus 1, 20. So 25/20, I can reduce that to be 5/4. Okay, so that's my B value. Okay. My C value, set the denominator equal to 0. I get x equals -1. Cover up the corresponding factor in the denominator, and then replace -1 in for all the remaining x's. 2 times 1 minus 7. -1 times -5. 5. So C equals -1. That's the hard part. Now it should feel a lot easier because you're just doing a bunch of natural logs to get to your answer here. Yeah, the denominator is positive, but the numerator is negative. And then all these linear factors in the denominator makes it easy use substitution and easy natural log integrals, right? So thankfully, the AP exam doesn't do anything more than linear factors. The quadratic factors can feel a lot more complicated, but we can skip all that because it's not a BC topic that they're going to put on the exam. So we just have to worry about the linear factors. Okay, so let's see if we can get through all of page 6, just so we can get really comfortable with this process. But then once you get it, it's easy, right? You're just repeating the same process. Once you can identify the need for partial fraction and okay. All right, so start with number 1. Okay. I'll go through each problem with you, but I want you guys to try it first and see how you do. Again, you know that partial fraction is a possibility if your denominator has a higher degree than your numerator. Yeah, so if the numerator has a higher degree, then we have to look at another option first. Maybe it's long division or something like that, right? But we know it's not going to be, partial fraction won't be the first step in the process if your numerator has a higher degree than the denominator.
But if the denominator has a higher degree, you said, I mean, you're implying that partial fractions don't always work when the denominator's degree is high.
That's a good question. It's not always going to work, but if you see it on the AP exam, it'll be a multiple choice question. So the hope is that you can look at the answer choices to kind of help give you a clue as to, oh wait, this is probably partial fraction because of the way the answer choices are showing up. Because I mean, it could be arc trig, right? With the denominator being, so I think the best way to tell is it's either trial and error or you look at your answer choices to help you decide which path to go down.
Oh.
Yeah. You could represent number one as a single natural log expression by pushing that 3 up as an exponent, pushing the 2 up as an exponent, and then treating this as the difference of two logs, which you can write it as using quotient property. Now, if it's true response, either answer is acceptable, but typically if it's on the AP exam, sometimes they like to use properties to condense their answer a bit more. So I just want you to be comfortable recognizing those.
division form, reference to the coefficients.
Oh, the coefficient gets pushed up first as exponents, and then you can do hash log of A minus hash log of B. Yeah, so the coefficients get pushed up first. And we'll just finish up with 3 and 4 for today. Just want to point out something. Right now, all these U values are really simple, right? There's not going to be any leftover coefficients, but imagine if it was something like integral of 1 over, 4x or 2x minus 1, right? You got to make sure you take out the correct coefficient from that U substitution. I know we don't see it here, but got to keep track of the fact that the 1/2 is going to come out from that U substitution. But right now, all of our U values are just nice, simple linear functions with no leftover coefficients. So, yeah, just make sure that if something like this occurs, you gotta take an extra step and make sure that you're keeping track of your coefficients from your U substitution. Everybody good with 1 and 2? Okay, so any questions? Okay, we'll do a few more of the classroom problems tomorrow before we jump into the next section. But I think there's enough for you guys to be successful with your homework and your AP practice. So check your calendar for your homework. Make sure you also do your AP practice problems as well. Okay, all right, forget your phones.
It's so. He's so good. I haven't watched the movie. You haven't watched it unless I've read the book. And
I just got something. Roman. I was looking at this. I think he's great. It's a lady version. It's so sweet, but it takes place in America, which is. Oh, it's American?
yes, it's American. It's mid-civil war. It's like 18. No, I like when it's, I like when, yeah, I like when it's in like, they have a little British shot. They probably have a British shot. I like the weird. And like, they're like the middle of Massachusetts, like, it's supposed to be, it's not. It's usually supposed to be. So, reasons for it. And that was. Oh, it's perfect. It's oh, yeah. I don't think Massachusetts, well, like Boston. I don't think they had a Boston.